All right, let's talk about it. Syringe contains this many moles of gas for this much volume. What volume will the syringe hold if 0.35 moles of neon are added? So this is a V1 over N1 equals V2 over N2 type problem. As we talked about last time, you don't have to remember these various relationships. All you have to remember is the ideal gas law. You can figure out all the other ones. So let's do that. Let's say you didn't remember this, which, anybody remember what the name of that law is? That's Avogadro's law. Let's say you didn't remember this. How do you figure this out? Well, you look at the ideal gas law, which most people seem to remember pretty well. PV equals nRT. And you realize that R is a constant, which means the other things must always be in relationship to that constant. So we can rewrite this as R equals PV over NT. Okay? And that means that PV over NT always has to be constant. Now, if you're not looking for all those and you only need a couple, like in this, you can say, okay, I need a relationship between volume and moles as one changes. And you can see the V's on top, the N's on the bottom, so it must be V1 over N1 equals V2 over N2. Right? Similarly, if you had a relationship between pressure and temperature, well, P over T equals P over T. Right? So as long as you can do this, you'll always have those relationships, realizing that those must stay constant. So that said, let's go through this problem then. We've got 750 milliliters. Actually, you can leave this one in milliliters, but just for consistency's sake, better to always use those same units, right? And 0.65 moles is V2, which is unknown, over N2, which is 0.65 times or plus 0.35, which is 1.00 moles. Yeah? Okay. So V2 is going to be 0.75 divided by 0.65, since that's just one, which is 1.15 liters. Or 1.2 if it's...
Hey, I have a question.
Yeah.
I have that on my test. I have the points. It's just not circled.
Maybe. At least some of them. What else did you do, if you don't mind?
Because I put, instead of putting 1 mole, I put 0.35. But I thought that when I, for some reason I decided to do 1 mole, because I thought maybe that's right. But I thought that number was too big. So I just didn't know what to do. So I just have both answers.
Okay. Well, you get some credit for it. Okay, any other questions about this one?
Why is it over 1 mole? Because it's 1.035.
Because 0.65 you had originally, and then the 0.35 is added. So you got plus 0.35 is 1.00. Right, so you added another 0.35 moles. And remember that the identity of the gas doesn't matter. All gases have the same volume with for the same number of moles. Other questions about that? Yeah. Yep.
Okay.
Yep.
And then just add, and it comes up at 0.40, and just add that to the 0.75 or whatever, and then it comes out to 1.15 liters. That's okay?
Yeah. Mm-hmm. That's just true. Yeah, doing the algebra before instead of later. Mm-hmm. All right. Reaction. So let's balanced equation. Magnesium metal. I guess I don't grade too carefully about whether or not you have the little indications there, but let's put them in there to be totally correct. So you've got magnesium with hydrochloric acid, produces hydrogen gas and magnesium chloride. Okay? Is that balanced? No, what do we have to do? 2 HCl. Then we're good? Okay, great. If 243 mLs of gas is collected at 25 C and 745 millimeters mercury, what mass of hydrogen is produced? Okay, let's use our ideal gas law. And we want to find moles. So N equals PV over RT. So that's going to be 745 millimeters of mercury. Let's do that conversion. 745 millimeters of mercury times 1 atmosphere per 760 millimeters of mercury. By the way, the reason I didn't have that on there, that is a conversion that you have to know. I just didn't say that last time, but in the future, you should know this. That one and the 273 Kelvin are going to come up a lot in these kinds of problems. So 745, I got a calculator today, so I can do my own calculations. That is 0.98 ATM. So that's going to be 0.98 atmospheres times 0.243 liters divided by 0.08, what did I say it was? 206 liter atmosphere per mole Kelvin times the temperature. 25C is 298 K. All right, so we do that calculation. 0.98 times 0.243 divided by 0.08206 times 298. And I get 967 moles. 967 moles. Yeah. Yeah. Yeah, that one was wrong. So that's why oh, if you use that one, that's fine. Yeah. Okay, it wasn't far enough off, yeah. All right, so that's moles, and now we need to know the mass of hydrogen. So we go 0.0097 moles of hydrogen times about 2 grams per 1 mole, right? Because H2, 1.0 or 2.02 if you prefer. And that's going to get you 0.02 actually. Or we'll say 0.020 grams of hydrogen. Okay. All right, on to the next part. If we start with 5 ml of the hydrochloric acid solution, what was its concentration? Now this one's a little bit tricky, a little bit backwards from what we usually ask in these kinds of things. But it's the same idea. You need to get your moles, and then you use the equation for concentration, molarity equals moles over volume, to get the concentration. So if we ended up with 0.0097 moles of hydrogen, how many moles of HCl did we start with? Twice as much, right? So it's 0.0097 moles of hydrogen times 2 mole of HCl per 1 mole of hydrogen. That's our molar ratio. And that's going to be 0.0194 moles of HCl. All right. So now we know that concentration, or molarity, equals moles over volume, right? So we've got moles, and we've got volume, 5 mLs. So the concentration of HCl is going to be 0.0194 moles divided by 0.005 liters. And that gets us 3.88 molar or something in that area. So that was the concentration of hydrochloric acid that needed to be used.
This was out of how many?
8, but I'll scale it to 10, so everything will be worth, accordingly. So if you got 6 out of 8, that's 75%, 7.5 out of 10. Questions? Okay, let's move on. So we've already actually done a lot of this stuff from this beginning, which I did on purpose in the problem session on Monday, but also today in the quiz. You've already done stoichiometry with gases. It's nothing different. It's nothing special. It's the same stoichiometry problems we've been doing. It's the same limiting reactants. It's the same moles. It's the same equations. We're just using gases now. And the only thing you need to know about those gases is that at this standard temperature and pressure, which is 0 degrees C, or 273 K, and 1 atmosphere. Pretty easy to remember, and you do need to know that. At those conditions, the molar volume of an ideal gas is 22.4 liters. That means that at STP, any ideal gas has 22.4 liters per mole. So we have a molar mass. Now we have a molar volume for a gas. Doesn't matter what gas, they're all the same. Remember that number. Remember 22.4, and remember those numbers for STP. 0 C, 1 atmosphere. All right, and here's a warm-up problem to get you going after the quiz. Well, let's do this one together, or you can do the next one on your own. Quicklime, calcium oxide, produced by the thermal decomposition of calcium carbonate. Calculate the volume of carbon dioxide produced from the decomposition of calcium carbonate to form 152 grams of calcium oxide. So far, you should be able to do these kinds of problems in your sleep, right? These are this regular old stoichiometry, limiting reactant stuff that we've been doing for weeks. The difference is we're making a gas. So we have to think about this gas in terms of molar volume. The rest of the problem is the same. Calcium carbonate decomposes to form calcium oxide and carbon dioxide. What's the first step? Balance it. Is it balanced? It is. That makes it easy. Good. Okay. So now what do we know? We know the amount of calcium oxide produced. That's all we know, right? So maybe write that down. 152 grams. And we want to know the volume of carbon dioxide produced. So what do you think we do first? Find out moles. That always seems to be the first thing, right? That's good. It is always the first thing, pretty much. So 152 grams of calcium oxide times, let's see, calcium's about 40 and oxygen's a 16. So that's going to be 56 grams per 1 mole. Actually, I think I have this one here. And that is 2.7 moles, right? All right, 2.7 moles calcium oxide. Okay, so then how many moles of carbon dioxide do we produce? Same amount, right? It's 1 to 1 by the equation. So this question mark, so far, is 2.7 moles. Now what do we do?
Use the ratio
Close.
and find the moles of the
Yeah, we found the moles of carbon dioxide, but what is the question asking us? It's asking us for volume at STP. So what do we do? How do we do that? We could use PV equals nRT, but there's an even quicker way to do this. we can use that molar volume that we just talked about. So yes, you could do the ideal gas equation here. Although you couldn't actually, because you don't know. Oh yeah, you do. Oh, you don't know the no, it's standard temperature and pressure. You do know the temperature. Yeah, so that would work. But the easier way to do it is to realize that there's this molar volume, 22.4 moles per liter at STP, always. And so that gives us 60.5 liters. Wait, no. Let's try that again. 2.7 divided by 22.4. 0.12 liters, so 120 milliliters. Ah, you're right. I'm sorry. I thought that looked wrong. I was like, something's wrong here. Thank you, thank you, thank you. 22, whoops. 1 mole has 22.4 liters. That's the right. Okay, so that's 60.5. Sorry. And this would also work in the ideal gas equation. You could do that also. Okay. So this next one is trickier. Let's set it up and then you can try it. So a sample of methane gas has a volume of 2.80 liters at 25 degrees C, 1.65 atm. Was mixed with a sample of oxygen gas having these other things, ignited to form carbon dioxide and water. The mixture, calculate the volume of carbon dioxide formed at pressure of 2.5 atmospheres and a temperature of 15 degrees C. Wow, okay. So, a lot of stuff going on here. What's the first step, do you think? Write the equation and balance it. So methane is CH4, and it's reacting with oxygen to form carbon dioxide and water. Is that balanced? No, how do we balance it? Right. Okay, now that's balanced. So what's next? What do you think you're going to have to, what sort of quantity do you think you're going to have to find here? Grams, liters, moles. What do you think we find first? Probably moles, right? Yeah. But now we've got moles of gases. So to find moles of gases, we don't use molar masses, we use the ideal gas law. So we've got this information here that tells us about the methane, right? And then we've got this information here that tells us about the oxygen. So from each of those sets of information, we can use the ideal gas law and find moles. All right, so see if you can go from there and finish this problem. So you're going to find moles, find the equivalents, calculate the volume of CO2 formed, and see what happens. All right, let's get those initial numbers and then go from there. What did you find for the moles of methane? Okay, we'll go with 0.189. Okay. Is that not right? Okay. All right, good. How about oxygen? How many moles of oxygen? 1 point what?
783.
Okay, great. So then how many moles of carbon dioxide do you form? Why half of the oxygen?
Because oxygen is eliminated.
You sure about that? Well, let's look at it. So if, yeah, right, because double this would be how much it needs. So this needs twice that of oxygen. There's actually quite a bit more oxygen there. So we go with this. So we're gonna form 0.189 moles of carbon dioxide. Okay? So that's the limiting reagent. Yeah. Okay, so now we've got moles. Can we find volume? We can, using pressure and temperature. Can we use STP? Can we say it's just 22.4 liters? No, because we're not at STP, right? We're at some other pressure and temperature. So what do we have to use here? Ideal gas law. We can say PV equals nRT, and we can rearrange that to volume equals nRT over P. Okay, let's plug those in. 0.189 moles times 0.08206. You know the units on that. Times the temperature, which is 15 plus 273, or 290 K. Divided by the pressure, 2.5 atmospheres. What's 2.8? Oh, yeah, you're right. Sorry. Of course. And that is 1.79 liters. Or thereabouts. Okay, great.
Quick question.
Yes.
What relation did you use for the finding the moles of CH4 and oxygen?
We used the ideal gas law for that also.
What was it?
So this, it would be N equals PV over RT.
Oh yeah.
Okay, so you can do that for each one because we know P, V, and T in each case. And then, yeah, so we solve for moles that way. Okay? And then as we deal with kind of some of these algebraic manipulations, we can actually use this to find the molar mass of a gas. So if you take a particular volume of a gas and you weigh it, you can calculate the molar mass from that pretty easily. Let's look at some of these relationships. This is a good algebra review also. N is number of moles, right? Then N equals grams divided by molar mass. We know that the molar mass, M, big M, equals grams divided by moles, right? Which we say is N. So then the number of moles must equal the grams of the gas divided by its molar mass. If we then use this relationship, which we got from just the good old molar mass equation that we've talked about, if we substitute that into the ideal gas law, we get, so remember the ideal gas law, PV equals nRT. If we put this in place of N, okay, we can get PV equals G over the molar mass RT. Everybody see that? Okay. Now we can also say, we can also switch volume and molar mass and say that the pressure times the molar mass equals the mass per volume, RT. And what is mass over volume? Density. Oh, it says right there. So another way we can rewrite this is P times M equals density times RT. All right, and we can rearrange this to solve for molar mass. Divide everything by P, and you get molar mass equals density times R times T over P. So nothing fancy there, just rearranging, doing some algebra, moving some stuff around. But what we find then is if you know the density of a gas, which you can measure, and you know the pressure and temperature, you can calculate the molar mass or the molecular weight. So let's try one. You can also do it the other way, of course, right? So calculate the density of nitrogen gas at 125 C and a pressure of 755 millimeters of mercury. Now, how would you do that? So how do you calculate density if all we know is pressure and temperature? What else do we know here besides pressure and temperature that can give us density? The molar mass. What's the molar mass? 28, right? Nitrogen gas is N2. So the molar mass is 28 grams per mole. We can then use that in the previous equation. M equals dRT over P. Or that can be rearranged, right, to say D equals MP over RT. If you want to do the rearrangement step by step, you're not comfortable with that quick rearrangement of all the variables, that's fine. But that's how it goes eventually. The point is to get D over by itself. If you want to plug the numbers in and do it that way, that's fine too. All right, so let's calculate this out. So that's 28 times, can we use this or do we need to convert that? We need to convert it unless we use a different R. All right, so let's convert it. 755 times 760 per 1 atmosphere. It's going to be pretty close to 1. 0.99. 993 actually. Divided by R, 0.082 times the temperature, 125 C. That's 398. Okay. Do all that out. I believe that gives us 0.85. Now be careful here. This is grams per liter. What do we, which is a measure of density, that's fine, but what do we usually report that in? Milliliters, right? Or cubic centimeters. So let's do that. 0.85 grams per liter times 1 liter divided by 1,000 milliliters is 0.00085 grams per milliliter or per cubic centimeter, or 8.5 times 10 to the minus 4th. Grams per milliliter or grams per cubic centimeter.
So that capital N stands for the molar mass?
Yeah, it's confusing. Technically, when we talk about molarity, it's the variable for molar mass, because molarity is really concentration, so we should use C for that variable and M for the unit at the end. Does Sorry, we can use MW or something. I don't know. There's not, we're kind of running out of letters. They shouldn't come together too much in a weird way. Yeah. Sometimes molarity is given as like a cursive. Okay, the reason we do that, it's kind of a weird exercise because we just rearrange an equation that we've already known and talked about. Why do we care? Well, because we care about the partial pressures of gases. And the partial pressures of gases are proportional to moles. And so if we can find, sometimes we'll have to use some of these relationships to figure these things out. So that brings us to one of the simplest and easiest laws that we've talked about at all so far, Dalton's law of partial pressures. This is perhaps the most common sense law of all of the laws. All it says is the total pressure is the sum of the individual partial pressures of the gases. So the only tricky part is it kind of breaks this thing down into something called partial pressure, which we haven't talked about before. But the idea is each gas by itself exerts a pressure on the system, on the container. And then all the gases that are in there together exert an overall pressure. And so each gas has a partial pressure, and then there's a total pressure. And the total pressure is simply the sum of all the partial pressures. Okay. So fairly straightforward, right? The whole thing is the sum of all the parts. Great. And we can actually use our ideal gas relationships to calculate the pressures of each gas. So look at some of these relationships here. You've got pressure 1 equals, or let's start here. Pressure total equals P1 plus P2 plus P3. These are all the partial pressures. Okay. Then you've got each partial pressure is nRT over V, because we know that P equals nRT over V. So that's true for each gas. So therefore, we can rewrite Dalton's equation here using the sums of the gas expression, ideal gas law expression for each pressure. So instead of saying P1 plus P2 plus P2 V plus P3 plus P4, we can say N1 RT over V plus N2 RT over V plus N3 RT over V. And because they're all occupying the same container at the same time, temperature and volume are constant. So that's why you don't see 1s and 2s subscript on temperature and volume. What? Well, that's the total pressure is a total pressure, but each individual gas exerts its own pressure relative to the number of moles of that gas inside of the thing. Okay. So you group the like terms, meaning you pull RT over V out of the equation, and you end up with P total equals RT over V, which is held constant, times the sum of the moles. So what this is really saying is the total pressure is proportional to the total moles, which we already sort of know because we know that that's the case in the ideal gas law. But this is going to help us do some calculations, because if we know the moles of the individual gases in a container, we also know the pressures. So we can calculate the pressure of a complete container by knowing the moles of the gases, and we can calculate the partial pressures. And this is going to have some consequences experimentally for some things we're going to see in a little bit. Now we're making a couple big assumptions here. One, the volume of the gas particles isn't important. That's something we talked about last time. Any gas, no matter what it's made up of, is going to have essentially no volume compared to the container, because the molecules are so far apart. And then secondly, the forces among the particles aren't important. And we're going to see later why that's not entirely true. But for our assumption, that's what we're going to use. Okay? So then we can do these types of problems. Mixtures of helium and oxygen in scuba diving tanks to prevent the bends. For a particular dive, you got 46 liters of helium and 12 liters of oxygen, and then that's all pumped into a 5-liter tank. Calculate the partial pressure of each gas and the total pressure in the tank. Okay? So what do we do first? What do you think? What do we need to find to be able to figure this out? I'll give you a hint. It's the thing we always find. Moles, very good, right. So can we find the moles of helium and the moles of oxygen that were put into that tank? We can, right? We can go through the ideal gas law and calculate N for helium and N for oxygen. Is there a shortcut?
So 1 atmosphere pressure, so it should be 0.1 portion.
Well, you got to be careful, right? Because STP, don't forget the T. What's standard temperature? 0. So 25 is not gonna give us that nice shortcut. So we're going to use the ideal gas law. So we can say N of helium, or moles of helium, equals, equals PV over RT. So that's 1 atmosphere times 46 liters divided by R times T25C is 298 K. And that's 1.88 moles. Or 1.9, I guess. If we're fine. Okay. And we do the same thing with oxygen. One atmosphere. But now we have 12 liters. And that gives us 0.49 moles. All right. So now that's the amount we start with, the amount we put into the final tank. And the final tank, we know the volume, but we don't know the pressure. Right? And we can't use the ideal gas law here because we don't know. We know the overall volume, but we don't know. Well, okay, I guess, yeah, we don't know the number. We do now the number of moles. But what we can do is calculate the pressure from the partial pressures. So let's calculate these partial pressures the same way we calculate any other pressure, just one at a time. So the pressure, the partial pressure due to helium, is going to be the moles of helium times RT over V. All right, nRT over V. And the partial pressure of oxygen is going to be the moles of oxygen times RT over V. So it's just solving the ideal gas law for each individual pressure. And if we plug those numbers in, you get 9.2 atmospheres for pressure and 2.4 atmospheres for pressure of oxygen. Okay. The only thing that's changed here is now our volume is 5 liters because we've put them all into this new tank. So that's the partial pressure of each gas in the final tank. The total pressure is, as Dalton's law says, the sum of the partial pressures so that's 9.2 plus 2.4 atmospheres, which is 11.6. So we didn't have to do another ideal gas law calculation to get the total pressure in the tank. We just needed to sum the partial pressures. All right, and that's what Dalton's law basically tells us. So not that fancy. Okay, we're going to use this now for one more concept that is useful. Mole fraction. Mole fraction, again, is a pretty straightforward concept. It's just the fraction of one atom's or one molecule's type of moles over the total moles. Okay, so it's just a fraction, right? Like if you're calculating a percentage or something. Same idea. But now, doing some algebra here, again, you can say the mole fraction is the moles of one over the moles of the total. But you can also relate the mole fraction to the partial pressures. So the mole fraction actually equals also what we might say is the partial pressure fraction or something. There's not really a nice word for that. But you can use mole fraction to calculate pressure and vice versa. So let's look at how this, I don't think I explained that very well, but let's look at how that works in a problem. Partial pressure of oxygen was observed to be 156 torr in air when the total atmospheric pressure is 743. Calculate the mole fraction of oxygen. So think about what this problem is really asking. It's giving you pressures, measured pressures in air, and it's asking you to calculate the mole fraction. The long way to do that would be to calculate, well, you can't even really do that because you don't know the number of moles of everything else in air, right? We know the partial pressure, but we don't know the moles of oxygen, and we don't know the moles of all the rest of the air either. So we can't really do that directly using ideal gas laws. But we can do it using the idea of partial pressures and using this relationship that mole fraction of oxygen equals the pressure of oxygen divided by the total pressure. And that we have. So 156 torr, and it's a fraction, mole fraction is unitless, so the units cancel out. 743 torr, we don't have to do any conversions there. And that equals 0.209. So that's telling us about 21% of the air is oxygen. And we did that just by knowing a partial pressure and the total pressure. So now you can imagine we can do some fairly fancy calculations finding mole fraction just by knowing some pressure. And we're gonna do some things back and forth to show that, and then we'll take a little break before we get into kinetic molecular theory. All right. Another way we can rearrange that is to say that the partial pressure of a gas is the mole fraction times the total pressure. Or the number of moles of a gas is the mole fraction times the total number of moles. You don't have to remember all these equations or anything. Just these are different ways of arranging the same thing, of saying the same thing. Okay. So then we can do these types of problems, and let's see if we can figure this out. The mole fraction of nitrogen in the air is about 78%, 0.7808. Calculate the partial pressure of nitrogen in air when the atmospheric pressure is 760 torr. So how much pressure is nitrogen exerting on its container when the total atmospheric pressure is 760 torr? How do you figure that out?
760 torr, isn't that one atmospheric pressure?
Yes.
So 78% of that.
Yeah. Yeah. That's all it is. All right. The mole fraction times the total pressure is the partial pressure. Well, partial pressure of nitrogen equals the mole fraction of nitrogen times the total pressure. And that's 0.7808 times 760 torr, or 1 atmosphere, however you want to do that. And that comes out to, I believe, 593 torr. Okay? Fairly straightforward. Again, a lot of this stuff doesn't really settle in until you start doing a bunch of problems to practice how you can be asked this in various different ways. We'll do some of those on Monday after lab, but I would encourage you to start on the book yourself. All right, one of the reasons that this is important and why we talk about this weird partial pressures thing is that for a long time, it was the only way that you could really measure pressure, because you could collect gases over something like water. So here's an example of a setup of how you might collect and measure a gas. You are dissolving zinc in hydrochloric acid. It's an oxidation reduction reaction, redox reaction that produces hydrogen gas. You bubble hydrogen gas out of your test tube and down into a bath of water. And then there's an inverted beaker in there that collects the gas. And depending on how far that water is pushed down, you can measure the pressure, the overall pressure of the gas, and that tells you how much gas you have. But there's a problem. When you collect something over water, that hydrogen gas is not the only gas in that container, because there's also water vapor in there. So the total pressure inside here, am I jumping ahead here without? Well, we'll get into the sample problem. But the total pressure inside here is not just the pressure of the hydrogen. It's the pressure of the partial pressure of the hydrogen plus the partial pressure of the water from the water vapor. So if you didn't account for that water vapor and you were trying to figure out how much hydrogen gas you'd formed, you'd get a wrong answer because you weren't accounting for the pressure from the water vapor. Now, luckily, you can measure the vapor pressure of water at different temperatures, so that partial pressure from the vapor, and you can look it up on a table. So you can look up whatever temperature, and you know what the partial pressure from water is going to be. Here are a bunch of values in millimeters of mercury. And so that allows you to do these types of gas collected over water problems. A sample of solid potassium chlorate was heated in a test tube and decomposed. All right, so it forms KCl, solid, potassium chloride, and oxygen gas, already balanced for you. And then the oxygen was was collected by displacement of water at 22 degrees C at a total pressure of 254 torr. What did I say? Okay, 754, thank you. The volume of the gas collected was 0.650 liters, and the vapor pressure of water at 22 degrees is 21 torr. Okay, so it's kind of in between these two here. Calculate the partial pressure of oxygen in the gas collected and the mass of the KClO3 that was decomposed. So let's do that. What we need, we ultimately want the mass of this, and to do that, we need to figure out the amount of oxygen. We need to get moles, right? There's nothing yet in here that we can get moles directly from. First, we have to get partial pressure of oxygen. So let's figure that out first. How do you think we find the partial pressure of oxygen in this system? Let's think back to some of the stuff we know in this problem. We know the total pressure, right? We know the temperature. And we know the vapor pressure of water. Right, exactly. So you realize from Dalton's law that the total pressure must be the pressure of oxygen plus the pressure due to the water vapor. And we know the total pressure is 754 torr. And we know the pressure of water, 21 torr. So we just subtract. And get, so that's 754 minus 21 is 733 torr. All right, so that was it. We got the partial pressure of oxygen. Okay. Now the next part, okay, we got that, great. The next part asks us to do some stoichiometry to figure out how many moles and then how many grams of the potassium chlorate we started with. So how do we get from partial pressure to moles? Well, we already got partial pressure. So we're not trying to find the mole fraction here.
Don't you have to do the equation first?
What equation?
Displacement of water.
Well, we got that already. We accounted for the water with this 21 torr. And so we got the partial pressure of oxygen. So if we've got pressure of oxygen, we've got volume, and we've got temperature, how do we find moles? Ideal gas law, right. So we've got moles of oxygen equals the partial pressure of oxygen times the volume divided by RT. So let's convert that torr is 760 torr per 1 atmosphere. So that's 0.964 atmospheres. Okay. So we've got 0.964 atmospheres times the volume, which is given, 0.650 liters, divided by R times T, which is 95K. So that gives us 0.026 moles of oxygen. Whenever you're asked for something in these types of questions, ask yourself, what do you have? And if you've got enough stuff, you can always use that ideal gas law. If you've got temperature, pressure, volume, you can use that ideal gas law. Okay, we're almost there. So how do we get the mass of potassium chlorate now? Yeah, mole ratio. We have to find the moles of this from the moles of this. So let's do that. We've got 0.026 moles of oxygen. And our mole ratio is 2 moles of potassium chlorate per 3 moles of oxygen. And that gives us 0.017 moles potassium chlorate. And then how do we get the final answer here? Multiply by the molar mass. And that molar mass is actually 122.52 grams per 1 mole. 2.12 grams. Final amount. So let's review what we did here. We had total pressure and we had total pressure of or partial pressure of water, because we always know the partial vapor pressure of water. We can always look that up. You don't have to memorize that. You'll be given a table or the amounts that you need, but you can look it up. Then we subtracted to find the partial pressure of oxygen. Then we used the ideal gas law to transform that pressure into moles. Then we did a mole ratio, and finally converted to grams. Okay, so take, I don't know, how long do you break you need? 10 minutes? An hour? All right, we'll take 15. We'll come back about 5-2, 6-2, 4-2, and talk about kinetic molecular theory.